Atomic and Nuclear Physics. In this video, we'll discuss examples part 2. Consider the following example. Example number 4. A radio station broadcasts at 89.3 megahertz with a radiated power of 43.0 kilowatts. How many photons does the station emit every second? So let frequency F be equal to 89.3 megahertz or 89.3 times 10 to the 6th power hertz. The power of the radio station is 43 kilowatts or 43 times 10 to the 3rd power watts. Knowing the frequency of the wave, we are able to get the energy of the photon. E is equal to hf, which will give us 5.91708 times 10 to the negative 26 joules. Knowing the energy of a photon, energy per photon, and knowing the total power, the number of photons that the station emits every second, capital N, is just equal to power divided by photon energy, which will give us N is equal to 7.267 times 10 to the 29 power photons per second. Every second, the station is able to emit this many photons. Going on to the next example, we have the following problem. While conducting a photoelectric effect experiment with light of a certain frequency, you find that a reverse potential difference of 1.25 volts is required to reduce the current to 0. Find the maximum photoelectron speed. So the stopping potential V naught is equal to 1.25 volts. We're talking about electrons, so mass of the electron we already know. 9.109 times 10 to the negative 31 kilograms. Stopping potential or reverse potential difference, V naught. Electron subjected to this electric potential difference will give you an energy of EV naught. This energy is the one that depletes the kinetic energy of the photoelectrons that are produced. So KE max is equal to EV naught. M V naught, we are able to calculate the maximum kinetic energy of the photoelectrons, 2.0025 times 10 to the negative 19 joules. Kinetic energy is just equal to 1/2 mv squared. Knowing the kinetic energy, we are able to calculate the maximum photoelectron speed, 6.631 times 10 to the 5th power meters per second. Next, we have the following problem. Example 6. When ultraviolet light of wavelength 400 nanometers falls on a certain metal surface, the maximum kinetic energy of the emitted photoelectrons is 1.10 electron volts. What is the maximum kinetic energy of the photoelectrons when you have a different light of wavelength 300 nanometers falling on the same surface? So given kinetic energy for the first case, for the first light, 1.10 electron volts or 1.7622 times 10 to the negative 19 joules. For the first light, we have the wavelength lambda 1, 400 nanometers or 400 times 10 to the negative 9 meters. For the second case, the second light, wavelength of lambda 2, 300 nanometers or 300 times 10 to the negative 9 meters. Knowing the wavelength, we can calculate the frequency of light. So lambda 1, you have F1, frequency 1, C over lambda 1, which will give you 7.5 times 10 to the 14 power hertz. Lambda 2, we have F2 is equal to C over lambda 2, which will give us 1 times 10 to the 15 power hertz. Now, for the kinetic energy of the photoelectrons for the first case, Ke max 1, that's just equal to EV naught 1. Kinetic energy max 1 is also equal to HF1 minus phi, minus the work function of the surface. So, using EV naught 1 is equal to HF1 minus phi, we are able to calculate the work function of the material of the surface, 3.2073 times 10 to the negative 19 joules. For the second case, since the same surface is used, that means the work function that we just calculated will also be the work function for the second case. Ke max 2 is equal to HF2 minus phi. We are then able to calculate the maximum kinetic energy of the photoelectrons for the second case. Ke max 2 is equal to 3.4187 times 10 to the negative 19 joules or 2.1340 electron volts. Next, we have example 7. A hypothetical atom has three energy levels, the ground level and excited levels, 1 electron volt above the ground level and 3.00 electron volts above the ground level. So, ground state energy, and then the first excited state is 1.00 electron volts above the ground state, and the second excited state is 3.00 electron volts above the ground level. Find the wavelengths that this atom can emit when excited. So given these three energy levels, ground state, first energy excited state, second excited state, so that's E1, E2, and E3, possible transitions of the atom to emit photons are from first excited state, E2, to ground level, to E1. So, energy released or energy difference between first excited state and ground level, E1, E2 to 1 is 1 electron volt or 1.602 times 10 to the negative 19 joules. Then, another possible transition is from the second excited state to the ground level. So E3 to 1, that's 3 electron volts or 4.806 times 10 to the negative 19 joules. Also, from the second excited state, you can also that the atom can also transition to the first excited state. So, E3 to 2 is equal to 2.00 electron volts or 3.204 times 10 to the negative 19 joules. So these are the three possible transitions that the atom can make and release a photon from higher excited state to a lower excited state. So each of these transitions will produce a photon. Knowing that photon energy is just equal to HF, that means E2 to 1 is equal to HF, E3 to 1 is also equal to HF, E3 to 2 is equal to HF. So each one will give us a frequency of light. You have F2 to 1, 2.4177, 48264 times 10 to the 14 power hertz. E3 to 1, you have F3 to 1, 7.253244793 times 10 to the 14 power hertz. And then E3 to 1 transition, you have F3 to 1 frequency 4.835496529 times 10 to the 14 power hertz. And each frequency has a corresponding wavelength. C, speed of light in vacuum is just equal to F lambda. So for every F, there's a corresponding lambda. We are able to calculate three wavelengths for the three photons emitted. You have lambda 2 to 1, 1.241 micrometer. Lambda 3 to 1, 0.414 micrometer. And lambda 3 to 2, you have 0.620 micrometer. So that's it for now. We'll continue our discussion of the examples part in the next video. So thank you for watching.